of a nonlinear system. Okay, so LQR pole placement works only for linear systems. An example we saw what x dot equals ax plus pu. So here is how can we apply LQR pole placement to nonlinear systems. Okay, a typical nonlinear system, I can write it as x dot equals fxu, where f is nonlinear. It could have x square in it. It could have sine of x, cosine of x, some kind of nonlinearity. Okay, so what is done is the solution to this is to linearize the system about some operating point. Okay, so x0, u0. So let's say that there's a quadcopter, for example, that's nonlinear, but maybe it's operating at a certain speed and there's a certain control when it's operating in free flight. You use that point to linearize the system, and then you use the deviations from that point as a way to compute A and B. So that would be linear, and then you can use control on that. So what we do is we'll see how to do this. Okay, so what we'll do is x0, u0 is the operating point. We'll replace x0 x with x0 plus tx, u with u0 plus tu in x dot equals f of xu. In other words, x0, u0 an operating point, we would look at a small deviation of the state by delta x, a small deviation of the control, delta u. So we can write x plus dx, the whole thing dot equals f of x plus, sorry, x0 plus dx, x0 plus dx, u0 plus tu. Okay, now this can be written as x0 dot plus dx dot equals, there is something called a Taylor series expansion, which helps us to expand out f of x0 plus delta x. So that Taylor series expansion is f of x0. You might have seen this in a numerical methods class. u0 plus delta x, sorry, df dx. The df dx is at x0, u0 times x minus, rather I'll put delta x plus df du x0, u0 delta u plus higher order terms. So these terms will be typically delta x squared, delta u squared, and so on. So since delta x is pretty small, what we'll do is we'll ignore those higher order terms. These are all, we'll assume that they are close to 0, because if delta x is 0.1, then delta x squared will be 0.01. And so you just chop them off. Okay, so what we can do is we can rewrite this as x dot plus delta x dot equals f of x0, u0 plus this delta x. We can just keep it as it is. Okay, let's just keep it as is. df dx u0 u df du. Okay, now what we see is that this can cancel with this, because that's basically when x is x0, u is u0, x dot equals f of x0, u0. So we can cancel that, and whatever remains, I'm going to write it on a new page. Maybe I should put some things here. This is Taylor series, and then x dot 0 is f of x0, u0, steady state. Okay, let me just move this whole thing on the new page. Okay, so we are left with delta x dot equals df dx x0 u0 delta x plus df du x0 u0 delta u. This is where we will assume this is to be a, and this is our b. Okay, so delta x dot is a times delta x plus b times delta u. Note that this is no longer x, this is the deviation. So it's deviation from the operating point. And that's kind of important. If you don't do it that way, then you'll get errors when you do the control. So a is df dx at x0 u0, and b is df du x0 u. So this is the key equation which we need. Yeah, so we've seen that this is just a derivation, and I think the derivation is important is for you to understand that this is actually the deviation and not the state. Okay, so I'll show you how this can be done for the differential drive car. The differential drive car is something we've seen before. We've derived the equations of a differential drive car. The equations have a cosine sine term, so it's not linear, but we can linearize it using this technique. And so we'll do that next. Consider the differential drive car dynamics. Here we've seen that x dot equals v cosine theta, y dot equals v sine theta, and theta dot is omega. Here state is x, y, theta. Control is v and omega. You can control the forward speed as well as the angular speed. Okay, so the question is linearize the system at some operating point. So let's say that this is capital X, x0, y0, theta 0, and capital U, v0, omega 0. Okay, so the non-linearity is because of this cosine, the sine term. Okay, so we cannot use pole placement or LQR to control it. So this is how we'll do it. Okay, so we know that delta x dot is a delta x plus b delta u. A is df dx, and b is df u. Okay, so we need to identify what f is. So we can write x equals f of x dot equals f of x, where x is here. So x is x dot, y dot, theta dot, equals v cosine theta, v sine theta, and omega. Okay, so this is f. Okay, so I need to compute the gradient or the first derivative, or if you like, Jacobian of f with respect to x, and the Jacobian of f with respect to u here. U is actually capital U. This is capital X. This x is the same as here. And this u is phi omega. Okay, so let's do that. Let's compute df dx and df du. Again, f is v cosine theta, v sine theta, omega. So df dx is, so remember, x is x, y, theta, right? So we need to take the derivative of the first term, v cos theta, with respect to x. So that is 0, 0. And so derivative of, you know what, let me write this so that you later on when you refer the notes, you are not confused. V cosine theta, cosine theta, dy, dv cosine theta, d theta. Then we have dv sine theta, dx, dv sine theta, dy, dv sine theta, d theta. Then d omega dx, d omega dy, d omega d theta. So that is, okay, clearly dv with respect to x is 0, 0. The derivative of cosine with respect to theta is minus v sine theta, 0, 0, minus, sorry, plus v cosine theta, and then 0, 0, 0. That's df dx. Then we have df du. So that, again, I'll write it down. So f dv cosine theta du, dv sine v cosine. So I need to take v and d. dw dv sine theta dv, dv sine theta dw. The last row is omega, so d omega dv, d omega d omega. Okay, so we can see that this is dv cosine theta with respect to dv is cosine theta. V cosine with omega is 0. V sine theta with respect to dv is sine theta. Next term is 0. This is 0. This is 1. So that is your, so this is your A. This is your B. And then this is the operating point, right? So you need to put it at x0, u0. So this will be 0, 0, 0, 0, 0. So not there. This will be x0, u0. So it will be at cosine theta 0. So what I have there is a constant because you give some, put in some values for cosines and sines, right? It's an operating point. So that is the linearized dynamic. So this is A. I'm almost done. Almost done. So this is A. This is B. Let me just write down the final expression here and then we're done. So delta x dot equals 0, 0 minus v 0 sine theta 0, 0, 0, v 0 cosine theta 0, 0, 0, 0. That's dx plus cosine theta 0, 0, sine theta 0, 0, 0, 1, u. And note that this is how to use this. The u, the total control, would be u0 plus delta u. In other words, this would be v0 omega 0 plus delta u, whatever comes from this controller, delta equals minus kx, so minus k delta x. This part comes from LQR pole placement. But this part, the first part, comes from whatever you had for the nominal control. And this u goes to the diff drive car. So don't assume that this is the total control. It's just a part of the control, needs to be added to the local control. Okay, get the LQR controller for a differential drive car. So I'll provide you with this file, diff drive LQR. It's just a file which computes LQR gains. If I run this, it just prints out the LQR gains. I actually also did it with pole placement. Okay, I did it with pole placement. It also tells you the eigenvalues of the uncontrolled system. It's 0, 0, 0, which means that the system is neutrally stable. It's not stable, not unstable. And the rank is 3 of the controllability matrix. So what goes in here is there's some operating points which are defined here. There is the A matrix, which is just copy pasted from my notes. There's a B matrix, copy pasted from, again, from the notes. Then eigenvalue of the uncontrolled system, controllability matrix, that was 3. So it's controllable because the dimension of the system is 3. Right? State is x, y, theta, so 3 degrees of freedom. I place the poles at -1, -2, -3, and then k comes from using pole placement. And then LQR, here is LQR. Q is the identity matrix. R is the identity. So it's 2 by 2 because there are 2 controls. V for the linear speed, omega for the rotation, and so R is 1e negative times identity. So that gives me k, gain k, and that was what I printed. Okay, now you could then take this and apply this on a system, but I've not done this in my code. Now, what I'm going to do next is, by the way, let me just point out one thing though. What we have shown you here is a different controller from what we learned in the part on feedback linearization. So if you want to do feedback linearization, which was something we've done in the past for I think we did it for the 2 degree of freedom system. We also did it for a pendulum. This can also be done using feedback linearization as follows. Okay, so just let me put that note here. So this controller is different from feedback linearization. So the way you'll do feedback linearization for the system, x start equals capital X start equals u. This is the equations of the car, where this is clearly x dot, y dot, theta dot equals v cosine theta, v sine theta omega. So if you want to do this using feedback linearization, you'll do x dot equals x dot ref plus the gain kp x. This is feedback linearization. Yes, so this is, why does this work. We have x dot minus x dot ref was kp 6. So this is, let's say, some epsilon. So we minus epsilon. So we have epsilon dot equals kp epsilon. So equation is epsilon dot plus kp epsilon equals 0. And then this particular equation, if you have epsilon dot equals kp epsilon or e dot plus kp is 0, that is basically an exponential decay. So if you start the system at some point, okay, this is epsilon, this is time, then this controller will ensure that this decays exponentially. Exponential. The other way to see this is there's a analytical solution to this. The solution is essentially epsilon equals epsilon 0 e raised to minus kpt. And you know that exponential, if it is with a negative sign, it will decay exponentially fast. Solution. Yes, so that's feedback linearization for you. It's a different controller from what we have here with LQR. Here, the equations of a manipulator are mq q double dot plus c q q dot times q dot plus g of q equals. Now, there's normally torque, but the way we'll write this is b of q times u. So dimensions. If there are m actuators, then we find a B matrix, which when multiplied with U gives you the right dimensions. Usually for a manipulator, B of Q is simply B. It's a constant. It will have ones in suitable places such that B times U would give you what you desire, which is torque at joint 1, torque at joint 2, and so on. Okay, now what we've seen is how to do linearization for this system. Seen how to linearize this system. X dot equals f x u. But that equation up top there for the manipulator is not quite like x dot equals f x comma u. So first thing, we need to convert that equation to look like x dot equals f x comma u. Okay, so first of all, that equation x dot equals f x u is a first order equation, and we have a second order equation here. So first thing first, we need to convert a second order equation to a first order equation, or in this case, two first order equations. So let's treat x as q and q dot. Okay, so this is just you can use x, choose x to be whatever you want. So we'll choose x to be q dot, where q is the angle and q dot is the angular velocity. So then if you want to compute x dot, that's going to be q dot, q double dot, just the derivative of that. Okay, now what I'm going to do is I'm going to write q dot as well. Q dot. Okay, q dot equals q dot is It's correct, right? And q double dot, the second line or second row, can be obtained from this equation by solving for q double dot. So if you see that equation there, it'll look like this. You'll have to move these two things to the right, and then multiply both sides by m inverse. So m inverse q let me write, okay, minus c q dot minus gq then I have plus pq. I think that's about it. Okay, now this is my f of x u, or rather write like this: f1, f2, that is, all the q's can be plugged in. This q dot and q can be written in terms of x, and then you'll have this equation. So now it looks like x dot equals f of x comma u. So once we have it in that form, we're now ready to do the linearization. Okay, so let's do the linearization. It's going to be a little bit complex because of this term. This is a complex term because there's a m inverse, and okay, but let's see how to do it. So we know that, just do it on a new page. So a equals df dx and we know that f is f1, f2, which is q dot m inverse q minus c q dot times q dot minus gq minus pq. Okay, so x is q dot. So everything here, whatever I've written down so far, is from the previous page. Now let's compute df dx. Okay, so I'll just do it slowly by not skipping any steps. So f has two rows, f1 and f2. So it'll be df1 dq, df1 dq dot, right? Because there are two independent variables, q and q dot, and those are the ones which I've used in the first row. Then we have df2 dq, df2 dq dot. Okay. Okay, so what's f1? F1 is q dot. So when you take the derivative of q dot with respect to q, you'll get 0, because q dot is velocity and you're taking the derivative with respect to position. Then we have f1 with respect to q dot. So velocity with respect to q dot, that is going to be simply 1, or identity, depending on how many q's are there. If there are more than one q, that's more than 2 degrees of freedom, or more than 1 degree of freedom, then you'll have an identity matrix. Okay, then we have df2 dq. Okay, so we need to take this thing here and take its derivative with respect to q and then take its derivative with respect to q dot. Okay. Okay, let's just do that separately because it's going to take taking this derivative is going to take me some time. So let me do that separately and then sub in the value here. So if I do, just let me write it as is, and then let's do it below. Let's do that. So I need to do d of dq of f2. F2 is this row, the second row of f, m inverse. I want to skip the functions. That way it'll be easier to write things down. Just remove the parentheses. I think this is wrong. This is plus p. Okay, so when you take the derivative of a product, you need to use the chain rule. So it'll be dm inverse dq, and then keep the entire thing as is, g plus. Then take the derivative of the second part, the chain rule. So dc dq q dot dg dq dpu dq. Okay, so now this term is actually m q double dot, right? Because that's basically the equation. This term on the right side is, go back, when I move things on the right, it's still mq q double dot. So that is mq double dot. And then when we're doing this, our assumption, just to make our life easy, is that when you're controlling a manipulator, the acceleration is zero. Okay, now this is what I'm going to show you is not true when the acceleration is non-zero. But let's assume that we are only controlling the system when the acceleration is zero. So this is zero because we are looking at steady state. The velocity can be non-zero, but the acceleration is zero. So that actually makes the life kind of easy. Otherwise, having that term and having this term, it becomes pretty complex. Okay, next is this part. Okay, so B is so B is a function of Q. So this is, so I think I wrote it down here. B is a function of Q. So this part is not equal to 0. G is a function of Q. So that is not equal to 0. And then DC, you can see that C is a function of Q, Q dot. So that is also not equal to 0. So that term remains. And so df2 dq is m inverse dc dq q dot. If B was constant, which actually it is for a manipulator, because the torque is not state dependent, it's just a constant, it will actually be 0. But let's keep it that way. So df dq. So we figured out this part. Let's call that 1. That's right here. Okay, let's figure the other part. df2 dq. Should have written this as dq dot, my bad. This is dq dot. So let's do that. df dq dot. So F2 is M inverse Q minus CQ Q dot minus GQ PQU. Okay, now technically you need to do chain rule, that is do dm inverse dq dot and then this one, but turns out that when you take the derivative of the first term, we just write this down as is. Okay, now Qm is only a function of Q. It's not a function of Q dot. So this term, thankfully, is just 0. So that's the first part of the chain rule. We really didn't have to do it here because M inverse is a function of Q. And then plus, now we keep M as a constant and then take the derivative of this whole term with respect to Q dot. So we have minus TC dq dot Q dot minus dg dq dot plus dpq dq dot u. Okay, now here also this term will be 0 because g is a function of gravitational torque, is a function of position, not a function of velocity. That's 0. This term is also 0 because b is either a function of q or it's just a constant. So we're left with only this term. So thankfully, this term is fairly straightforward in some senses. Minus dc dq dot q dot times q dot. Okay, and then let's call that number 2. We just need to plug that number 2 in here. And then by doing this, we have evaluated A to be an n by n matrix. Wait, it will be n by n. Okay, now we're left with B. So B is df du. So df1 du, df2 du. So df du of f1, if you go back, f1 is just q dot, and f2 is this complicated thing. So let me put those things down. So dq dot du, and then df2 would be m inverse minus c q dot minus g plus pq. Okay, now comes the time where we can cancel this because because that's a function of q dot, and when you take the derivative with respect to u, that's 0. And then when you take the derivative of this part, you see that m is a function of q, so there's no real need for chain rule. This part will be 0 because it's only a function of q dot. This will be 0 because g is a function of q. You're only left with this part, the second one, and that I'll just write it down below. This will be 0. M inverse q pq. Okay, so now we're all set to write the equations. We have delta x start equals a delta x plus p delta u. That would give me, in that form, a would be 0 minus m c minus g plus pu. Oh, hold on. That's not true. Just get this. Once here. Okay, let me write this down as is. M inverse be a plus here minus dc dq dot dq dg dq plus db dqu identity, and then M inverse dc. Now, if you needed, you could also make a further simplification. This, remember, is, should put a q dot here. If q dot is 0, that is, if not only is the acceleration 0, but the velocity is 0, then you can actually simplify this. You can just cancel this off. If this term goes off, if you know for sure that q dot is 0, and then this term will also be equal to 0, and so you'll end up with a much simplified term, but only if q dot is 0. It's an I. This is an I. Matrix. Okay, and then that's A, and then B is so when you're trying to do this control, normally you're trying to hold a steady state. And if you're holding a steady state, that is, position is fixed, velocity is 0, acceleration is 0, then only then these two terms will actually will be 0, and then it'll be much simplified. So the system I'll show you, we're actually trying to do that, trying to keep a pendulum upright, in which case those terms will actually be 0. Okay, so that's that. Let me write B and then show you an example of a system which uses this control. So here is the last step, B. Is df du, and this is just a summary of what I wrote down. This will be 0 m inverse pq times u. There's no u, sorry. That's it. Yes, let's see an example of this. Okay, what do you mean by underactuated? Let me explain that. We'll look at a system of a double pendulum system. So let me draw it like this. The two pendulums I'll look at. Okay, so two joints, 2 degrees of freedom. Let's say these are Q1, Q2, same for this one. Okay, now normally what we've seen so far in this course, when you did inverse kinematics, dynamics, Cartesian control, and so on, we put 2 torques at the 2 joints. So that system is called fully actuated. You have n degrees of freedom, here 2, and then you have 2 actuators, and so you can completely control those 2 degrees of freedom. However, what if you only had 1 actuator? So here, for the left case, you have an actuator, only 1 actuator at Q1. Okay, here we have only 1 actuator at Q2. 2 degrees of freedom. So 1 is less than 2. POF. Again, 1 less than 2. Actuators, number of actuators less than degrees of freedom. So these systems are underactuated. You can see if you have less actuators than the degrees of freedom, it just becomes harder to control because you can independently control that. So imagine that you had, like your hand, you can control your elbow joint and shoulder joint, and you have torque. So you can do many things with that. But if you are incapacitated with you did not have a muscle on your elbow joint, then it becomes so hard for you to control your elbow indirectly, right? Directly, right? Because you don't have an actuator. So it will happen if somebody loses their hand or from the hand from the elbow, then that would be the case. You'll have to, of course, put a prosthetic, but if you don't have power on the prosthetic, that part of your hand becomes underactuated, and then it's just difficult to control. These systems have names. The first one is called a pendubot. Okay, and this one is called the acrobot. Okay, the acrobot signifies somebody on one of those an acrobat who's freely swinging. So if an acrobat is swinging on one of those poles, then the person can apply a torque using its body joint. So this is the person, but they cannot apply a torque with their hands, and so that's why the name acrobat. So think of, this is a person's hand, this is a person's body. You can only torque the body, but you cannot put torques at your hands. So I'll show you how to control the system. It turns out that we can use LQR. So the trick is linearize. Step 1, 2, use LQR. The controller would be minus K1 Q1 minus K2 Q2 minus K3 Q1 dot minus K4 Q2 dot. Okay, so LQR will give this, and I can tell you that this is not very intuitive. It's just very hard to guess a controller for underactuated system. It's not that trivial. So let me show you how to do this with LQR. So first linearize, which I did. I basically have like a code which will do this for you, and then once you do that, once you have the linearization, you can use LQR. Okay, so this is the code which generates the equations of motion. This is taken from some of the very early notes I had about dynamics, where there were 2-link pendulum. So it gives me the mass matrix, the Coriolis term, the C, and then the G. So this part, up till this part, is something we've seen before, that is the equations of motion. What is new here is computing the linearization. That's done next. So then I have dg dq, dg dq dot, dc dq, dc dq dot. Okay, and then on this. Just thinking. So mass m1, m2, c1, c2, g1, g2. Now comes the part where it does the linearization. So once you get this, I took this, took my earlier code, which is the pendulum with dynamics, and then put the linearization here. It should be somewhere here, A, B, Q, R. So here it is. So this is the linearization. This is just copy pasted from that earlier result. And then this basically gives me the linearized A and B matrix that is used by the function LQR. So this is LQR. It basically computes the gain K based on the Q and R you provide. First, let me just run this and you can see what. So here it's just balanced, and you didn't quite see I actually pushed it by 0.5. Let's do that again. There's nothing interesting going on here, clearly. Let me go. Okay, so there's nothing going on. Let me just push this by 0.5 on the first link, and I think it goes crazy. So this is like pushes the elbow joint, so the shoulder joint, and then it goes crazy because there's an actuator at the. This is an acrobot, by the way. So there's an actuator at the connection between the red and the blue link. So it's really hard for it to balance. But if you give the same thing for 0.5 for the second link, that is the link, it can actually balance itself. Okay, so clearly this is valid only for some perturbations from the zero. If you do too much, this control will not work because it has a what they call a convergence region, and beyond that region it will not work. Now you could do something more interesting, which is I actually have a simulation so that it can actually apply a disturbing torque every single second. So think of somebody pushing the system in order to destabilize it. I think it should be right here. So I can set a torque deviation. I can set an angle deviation for the two angles and the or the velocity. So I'm going to give a velocity deviation. So this is basically and introducing some noise in the system. So because the system, the sensor noise, it has to fight the system and then get it to stabilize. You could also put a torque disturbance, and I think I put 40. But that's not stable. Yes, that's clearly beyond the region can stabilize. We can try something smaller. Oh, this is the first link, correct? First link is going to be a difficult one because there's no actuator. But let's try on the second link. It's not a failed too. There it's failed. That's too much. Try a smaller one. No, that fails too. There's some plotting error, but it looks like it's not doing that well. Okay, so there's clearly there is like a range where it can work, and it's not like a foolproof that because you find a LQR controller does not guarantee that the system will be stable, because remember that LQR, the linearization, holds about a particular equilibrium, the 0 point, and so if you're too far away from that 0 point, it'll simply not work.